Hi, I'm Yoav Weiss. I work at Google as part of the Chrome team. And I wanted to talk to you all today about a platform feature that I've been on and off working on and on and off thinking about for the last 2 years. And the reason for that is that I believe it can make the delivery of large JavaScript apps significantly faster. First, let me start out with a caveat. This is not here's a tool you can use today in your work kind of talk. This is more of a here's what the future may look like if I have my way talk. So in this talk, I will outline why JavaScript loading on the web today is not great. What are all the aspects in which it can be better, and how we are planning to tackle those aspects with new and exciting platform capabilities. Okay. So what's wrong with JavaScript loading today? The main problem is that we have a lot of it. Many websites and web apps today have a lot of JavaScript. The functionality that those sites require is getting more and more complex, and the code to support it is growing accordingly. Now, I could tell you all to ship less JavaScript, and if you can, you totally should. But that's not a long-term solution to solve this problem. On top of that, because we're all humans, we like to work with small chunks of code at a time in order to make them easier to understand and in order to be able to divide labor working on those chunks of code. And working with small chunks of code also makes it easier to reuse bits and pieces of them in various projects, whether those are homegrown pieces of code or open source libraries. But combining the fact that we load a lot of JavaScript and then we do that in small chunks really adds up. And ever since the early days of the web, we understood that requests have a cost. With HTTP 1.1, the browser was limited in the number of connections it was allowed to open to a single server, which resulted in those kind of waterfalls that Matt just talked a lot about. If you had many requests for sub-resources on a page, it took many round trips to bring all those sub-resources down to the browser. And we had high hopes that HTTP 2, or H2 as we fondly call it, will fix all the things. But reality proved to be a bit more challenging and complex than that. H2 was supposed to fix that, and to some extent it did. The cost on the network of each request is significantly reduced, again, as Matt shown. But that doesn't mean requests are now free. Each resource is still compressed separately, even with H2. So if you don't bundle small chunks of code together into a single larger chunk of code, the compression rates you will see are significantly smaller. And that is because compression algorithms rely heavily on backward references, essentially telling the browser, remember that long string you've seen before? Here's another one. And longer files tend to have a longer frame of reference and therefore can indicate strings that were seen much earlier and when those strings are a good fit, which results in better compression rates. But when files are really small, the frame of reference is also small, and compression doesn't do a whole lot. We tried to tackle that in the past with a proposal that would enable compression to work across different H2 streams, so across different sub-resources or different files. But that proposal never took off, mostly because compression can be risky when the context is shared between unrelated files. And there were concerns that such cross-stream compression would help to reveal secrets from some resources when an attacker has control over other resources on the same origin. So that didn't work out. On top of that, internal processing means that every extra request adds a cost. The requests are created in the renderer process, which sends them to the browser process, which checks the network service, which may or may not check the HTTP cache, which can add disk access costs and I/O costs. Service workers add a few more IPC calls to that equation, or inter-process communication calls to that equation, which adds yet more cost to each request. And if you have hundreds or even thousands of tiny modules on your page that you're putting together, that can result in a substantial slowdown in the order of 1 millisecond per request. As a result, people bundle their code using Webpack, Rollup, and other bundlers. These bundlers perform various optimizations on your content. They do code splitting, which is making sure that you don't have a single huge bundle for your entire site, but separate bundles per route or per entry point to your dependency graph. Hashing, which is making sure that your static assets have content-based URLs, enabling long-term caching. And various transformations such as image compression, text compression, dead code elimination, minification, transpilation, and more. Bundlers today also have multiple output format options, but all those output format options, either CommonJS or ES modules or whatever the one in the middle is, they all come down to a big ball of JavaScript. It's all a single JavaScript file, resulting in loss of any caching ability of the different chunks of code as a separate entity. And losing caching is bad because files change. If small parts of your JavaScript on your site have changed, now you have to invalidate the entire bundle and send down all the code, even the parts that haven't changed, back to the browser that now needs to reinterpret it, compile it, and all that has a visible performance cost. And modules can also be shared. Modules and chunks of code can also be shared across different entry points to your website. So if you have shared modules in one bundle, you can't really rely on that when downloading another bundle. You have to either include those chunks of code in both bundles or send them off to a separate shared bundle. But what's shared between different entry points can vary widely. And when you have a lot of them, the shared module paradigm can get real tricky real fast. And it's essentially more of an art than a science nowadays. So essentially what we have on our hands is a granularity trade-off. There is an inherent trade-off between bundling, which is great for the delivery of the JavaScript code, and caching, which is great to not having to deliver anything at all. Folks who bundle their scripts or the bundlers themselves now need to think long and hard about which modules and chunks they now have to include in each bundle to minimize the risk of cache invalidation that will drag the entire bundle down with it. And even if we bundle, we need to keep an eye on that granularity to ensure the trade-off is respected and we don't hurt delivery in favor of caching or hurt caching in favor of delivery. Another issue with the big ball of JavaScript approach is that execution cannot start before the entire resource was downloaded and parsed. When the network is constrained, that can add a significant delay to the time we can run the beginning chunk of the file if we had streamed execution in JavaScript. But JavaScript files can only start execution once the entire file was fully downloaded and parsed. Those are the language semantics. So while some JavaScript engines, such as V8, have stream parsing and theoretically could enable streamed compilation of JavaScript, the format doesn't allow us to have stream execution. That's not awful when your files are relatively small, but starts to get significantly slower when sending down huge, potentially hundreds of kilobytes, if not more, bundles to the browser. What that means is that the browser is forced to execute the bundle on the main thread when it fully arrived, which can result in long execution tasks initializing everything the bundle initializes, and those tasks starts relatively late because they wait for the entire resource to be downloaded. So if we'll talk about modules for a second, let's take this module structure as an example. Above, you can see like the dependency tree, and below you can see the order in which those different modules will execute. And therefore, the way that they are currently bundled into JavaScript blob, assuming that the bundler did its job correctly. So today in V8, if we assume to have stream parsing, the parsing part, so the red part in that diagram, can be done in parallel to the download, almost. But if we take compilation and execution into account, we can see that compilation is serial and happens after parsing is complete, and execution is also serial to compilation and happens only after compilation is complete. And this is slightly better for V8 than what happens with other JavaScript engines that don't have stream parsing, which can be even worse off here. And theoretically, we could have parallel compilation that happens in parallel to parsing. And that would give us a slightly better picture, but still, even though the parsing and compilation are now almost in parallel to the download, execution is still lagging behind. It's still serial to everything. And that means that effectively it requires the browser to download the entire resource, perform parsing and compilation on it, which supposedly now happen for free, but execution can only start at that point in time. And again, this is something that is potentially possible in V8, but other engines are further away from those kind of optimizations. But if we had a magical way to enable the bundle to be executed in parallel to the download, parse, and compile, this is what this would look like. This is what it would look like if we managed to maintain file-by-file granularity for those different chunks of code. So an engine with stream parsing would be able to start parsing straight away, and compilation and execution would finish shortly after the file has finished loading, rather than that start at that point. And that would also hugely benefit engines that don't have parallel parsing and compilation optimizations, as it will, in a way, reduce the importance of those optimizations because they only matter for the very first chunk of code. OK, so as the title of the talk suggests, I think that this magical format exists in the form of the WebBundle proposal. So what's WebBundles? It's a new format that enables you to wrap a bunch of HTTP requests and responses into a single file. If you're old enough, think MHTML, but without the ickiness of multipart. If you don't know what MHTML is, you're lucky. Just be grateful. While WebBundles can be used for all kinds of resources, I'm particularly interested in them in the context of JavaScript resources, as you may have guessed. And why are they so great? That's because having a single resource that contains separate, individually addressable sub-resources helps us solve that granularity problem and eliminate the trade-offs we just talked about. From a compression perspective, a web bundle is a single resource that can be compressed as such. That means that it enables us to have backward references from one resource to previous ones and achieve similar compression ratios to the ones we would get if we were to concatenate all of them together into a single JavaScript file and then compress, which is what Webpack more or less does today. The security questions that were raised by cross-stream H2 compression don't really apply here, because in the WebBundles case, the compression would happen on a static file as part of the build process, which doesn't include any per-user data, and as such can't be exploited to extract that data. So WebBundles will give us the same compression improvements that we see from Webpack today when comparing to the unbundled approach. When it comes to caching, we'll see a major improvement. The difference is that in the big ball of JavaScript approach, we are losing the individual file's identity in a way. We're giving up that granularity in favor of the compression and performance benefits. But in the web bundle approach, each file gets to maintain their own URL and their own caching header, potentially. Resources inside the bundle can have lower lifetimes than the bundle itself, if that's needed. And the content referencing the resources inside the bundle can modify itself to not reference one of them while referencing all the rest that it already has in its cache. This is one proposed way to declare sub-resource bundles. There are other competing proposals on the syntax front, but that is not critical in my view. Here we have a link tag that declares a bundle. And then later on, we have resources that refer to resources inside that bundle using their regular URL. This raises a couple of questions. The first question is, how can the browser know that the resources in the bundle are indeed inside the bundle before it downloaded the bundle? Because in that case, if you're a browser and you go over those, you create the DOM, or more likely scan those HTML tags ahead of time and see those URLs, there is no way for you to know that one URL is contained inside the other. The second question, if we're a browser downloading a bundle, how can we communicate to the server what's already in the cache to avoid re-downloading that stuff that's already in the cache but is in the bundle? Potentially, the browser could know that some resources in the bundle are not really needed while others are. How can the server know that as well and avoid sending those resources down? So as an aside, that's a slightly similar problems to the problems we had with H2 push, where many folks using it were pushing resources already in the cache, which was wasteful for bandwidth as well as the user's time. This is something we try to address for the H2 push case by proposing a cache digest that the client can send to the server. A cache digest is a probabilistic data set which represents all the URLs that are in the cache for a particular origin. It's using math magic to represent those URLs in order, like in a probabilistic way. So it gives us high confidence that the server will not send things that are not necessary to the browser, but there is an odd chance that it would, but statistically it's not significant. But eventually, as I said, this was a proposal. It wasn't picked up by H2 push implementers as they were not excited about the complexity implementing it entails, because they were generally seeing negative results from H2 push and weren't willing to invest more resources in making it better. One way to solve the two problems that I mentioned above is a scope attribute. So essentially, on each bundle, we'll define what scope it covers in ways that are very similar to a service worker scope. And that would enable the browser to match any outgoing requests that are in this scope to the web bundle declaration and not double fetch those resources before the bundle has actually arrived. And for that, if we wanted to notify the server side what's in the browser cache, we could do that using a scope-based cache digest. So in this scenario, the browser could keep track of all of its cached resources that are included in the scope and send a digest that covers those resources to the server alongside the bundle request as a header. This proposal seems to have a decent developer experience as the scope attribute is fairly small and contained. At the same time, it has some trade-offs when it comes to implementation, complexity, and cost, because this creating a scope, creating a cache digest for any arbitrary scope is not something that browser caches can do today, and is not something they are currently set up to do in the way that the information is arranged both in memory and on disk. So that proposal will require some significant changes there, or a parallel mechanism that will keep track of resources that are in or out of the cache. Another proposed alternative to scope is the resources attribute, which contains a list of resources that are contained in the bundle. Then the browser would be able to send either hashes or even a bitmap if we assume that the list is in order of the resources that it has in the cache to the server. That is significantly more efficient than the scope proposal, as if we go with a bitmap, that would mean 1 bit per resource in the bundle, which would result in significantly less overhead for the request. That also would be significantly easier to implement, as it matches more or less the way that current caches are structured. At the same time, in terms of developer experience, creating a list of all the resources that are contained in the bundle can be slightly cumbersome. Those lists are likely to clutter the HTML, and most probably they will require the HTML to be part of a build process and be generated, rather than have someone hand type those URLs one by one. So what I have in mind is to have a larger bundle, or a per route bundle generated at build time in a similar way to the way bundles generated by Webpack and Rollup today are being generated, only outputting a web bundle instead of a JavaScript blob. Then a dynamic server component would be able to take that bundle, take a request that the browser sent for that bundle, and use the information from the request and from the bundle to dynamically subset the bundle and exclude any resources that the browser already has in its cache. Note that the server can be stateless and doesn't need any information other than the bundle and the request in order to figure out how to do that subsetting on the fly. One glitch in that plan is that for static files, we get significantly more efficient Brotli compression levels during build time by using Brotli 11 that take up a lot of CPU time to compute, but it produces files that are 10 to 15% smaller. Sorry. So that creates another trade-off here between subsetting the bundles and sending the highly compressed originals. But I was fortunate enough to host an intern this summer that took a crack at this problem and managed to reuse the information that the Brotli compressor generates when compressing a bundle with Brotli 11 and reapply that on a subsetted version of that same bundle. In other words, we can reuse the compression information from the entire bundle and use it to compress the subsetted one, the one that doesn't contain a few chunks of code that are already cached. And the results we got for that are exciting. Up to 5.3 smaller, like percent smaller files for a subset when comparing it to on-the-fly Brotli 5 compression. At the same time, we had significantly faster compression speeds than Brotli 5. So that means that we can get both on-the-fly compression and high-quality compression when operating on bundle subsets. And this is all just like preliminary work. It will require some more productization in order for that to be part of the Brotli format, but it is exciting. And finally, when it comes to execution, with WebBundles, we can get file-by-file granularity we talked about and get almost streaming execution without any fancy JavaScript engine optimizations, just because we're dealing with smaller files. Now, a question that keeps coming up a lot, will this optimization require us to send ES modules down to the browser? And the answer to that is not really. This is a scheme that can be useful for any content that is composed of multiple small resources. So it can be useful for classical scripts. It can be useful to replace your image sprites if you're still using them. And in particular, for classical scripts, it doesn't need to rely on ES module dependency tree semantics at all. And currently, this scheme will be faster with classical scripts than with model scripts because module scripts don't really support streamed execution as long as we define the dependency tree because they need the entire module tree to be downloaded before they can start execution. But this optimization, this loading pattern is a requirement in order for us to actually have fast ES modules that are loaded in the browser. They're required for us to be able to speed up ES module loading. But on top of that, we will need some other changes to ES module semantics and the way that they are run in the browser. So we'll also need dependency tree delivery with the first module, at least that's arguably the case, or it depends on the height of the tree, because it could, if we don't have that, it could create some lag in the execution, but not necessarily a lag that, as big as the dependency tree. It will require ES modules to be able to eagerly execute before the full module tree is downloaded. And then the ability to run tasks between tasks and microtasks between modules, which currently is not there. So it will require a semantical change to ES modules in order to be able to streamingly execute them. So this work is something that, like I said, I've been thinking about that for a while. The WebBundles work is work being done by Jeffrey Askin as part of the Chrome team as a in a separate repo. I sent out I wrote a document that outlines this plan a few months back, and now Dan Ehrenberg from Igalia and Yuda Katz from Amber are collaborating with us on a subset of the broader WebBundles proposal that will enable that kind of resource bundles. The repo on the screen contains the latest proposal from Dan, which is slightly different in terms of syntax, but is largely compatible with what I have in mind. I intend to write down like a competing proposal, but on the same repo. So we're collaborating and trying to merge our proposals together in order to figure out the best parts of each. And if you have any feedback on that, if you have experience with current bundlers, or you would like to contribute to this effort, please hop over to the GitHub repo and file an issue, or or open a PR. We are hoping to move that repo to the YCG, the Incubator Community Group, fairly soon. Okay, so to sum it up, JavaScript loading is suboptimal. Bundlers today are doing what they can, but the platform needs to support them better. WebBundles can make things better. They can improve caching, resource sharing between bundles, and execution speeds without compromising on compression quality, which is wins all around. And fast ES module delivery will require some more work beyond just WebBundles, but WebBundles are a requirement for that. And with that, thank you.